All right, good morning. Welcome to the workshop or the deep dive into design patterns revisited in modern Java. My name is Venkat Subramaniam. It's great to be here. Thank you so much for joining this morning. It's absolutely a pleasure to actually meet humans in person. This is amazing. I'm almost in tears even saying this. It's been a long journey towards this recovery. So I'm really glad to be here. I'm very glad that you decided to join this morning. I want to talk about design patterns to begin with, and we got a lot of examples. But just to set the stage for what we're going to do, approximately we'll go for about an hour and 20 minutes, and then we'll take about a 20 minutes break, and then we'll continue for about another hour and 20 minutes. So we'll split the 3 hours into right about an hour and 20 minutes with enough time for the break in between. If you want to go around, use the facilities, refill your liquids, there'll be enough time for it. So let's get started. Well, we want to talk about design patterns. How many of us have used design patterns before? Yeah, that's everybody, right? In fact, I know some people actually had design patterns for breakfast this morning, right? So we all love design patterns. But I want to first talk about design patterns before we go into it. Let's talk about, grandma. We know grandma makes the best pie ever. And you've been telling all your friends about grandma's pie. And one day your friends tell you, well, if your grandma's pie is so good, why don't you make that pie for us? We're going to come home on Saturday. We're going to enjoy the pie, grandma's pie that you make. So you get pretty nervous. So you call grandma and say, Grandma, we're in a crisis. And grandma says, what's up? Well, my friends want to eat the recipe that you've been making. I've been talking about that to them. And they said I should make grandma's pie. Give me the recipe. And grandma says, oh, it's really simple. Take some flour, take some sugar, toss it in. Whoa, slow down, grandma. Tell me how much flour should I put? Tell me how much sugar should I put? And then grandma says, oh, about 2 sugar. Wait, is it tablespoon or teaspoon? You sit down and write the whole thing, and then you ask grandma, what are the best practices? What are the do's and don'ts? And you take all these notes, and you start early on that Saturday, and you make that pie. How did that turn out to be? Yeah, the little laughter I heard says it turned out to be a disaster, isn't it? In fact, the last time I tried something like that, I lost the utensils with it, lost a spoon with it as well. And I couldn't really recover it anymore. And you go to meet grandma the next weekend and say, Grandma, that was a disaster in the making. Your recipes didn't work. And grandma says, let's talk about it. And as grandma's having a good time talking to you, and you're watching grandma make pie, and what does she do? She takes 2 teaspoons of sugar, measures very accurately, and puts it right? No, definitely not. As she's having a good time talking to you, she's taking some sugar and tosses it in, and you said, whoa, what was that? She says, sugar. And you said, how much did you put? And she says, enough. And you realize grandma doesn't use the recipe she gave you. Well, what I'm trying to say is, the best book written ever, the Design Patterns book, remember that? Well, those 4 people, I would say, are the grandparents of our industry. And the worst thing they 4 did in their life, I think, is to write the damn book. Because the minute they did, everybody thought I could make the pie out of it. And then, of course, we know the rest of the story. So my argument is, if you wake up in the morning, and the first thought in your mind is, I wonder what design pattern I can use today, I suggest you call in sick. Tell the boss you've not been feeling well, you need just a day or 2 of break just to get over it. Well, now that I encouraged you so much about design patterns, let's talk about design patterns for the rest of the morning. Well, the point I want to emphasize is that I've never actually designed a software ever where I sat down and said, what design pattern I could use today? And in general, if I did it, it ended up to be a disaster rather than a benefit. And in general, though, I find that design patterns are phenomenal as a communication tool. but not as much as a design tool. And I think that's probably what separates the novice from the more experienced, I would say, is we jump into patterns in the beginning, but as time goes on, we realize that's a great way to explain what we are doing, great way to maybe summarize our thoughts, maybe to navigate towards a solution in the end, but definitely not something to start with. So I would encourage developers not to jump onto patterns, but maybe to really arrive at patterns and evolve towards it. That's maybe an effective way of using it. And design patterns, of course, are a great communication tool, like I said. That's what I really like about patterns is it's a great form of communication. In a way, I would say, imagine you have a drawing application. And in the drawing application, you want to place some squares, some rectangles, and maybe other objects. And what do we typically do with an application like that? One thing that really helps us is, as you're about to place a little object or an image, there is a grid, and it just snaps towards a grid, and that becomes easier to place things. So think of design patterns like a grid on which you can snap. So you're trying to find a solution, you're trying different ideas, but as you come closer to something that's to a design pattern, maybe you can click towards it rather than trying to really seek it in the beginning. And also what really complicates most of what we do is we typically don't end up with one design pattern. Usually a code may have a collection of patterns that interplay with each other, and that can really make things complicated as well in terms of how we can identify it. But having said that, patterns can be really useful as sometimes a cautionary tale, maybe do's and don'ts, things we want to avoid, maybe things that we could really think about and say, maybe this is something that's useful, maybe we could consider. But on the same token, though, I remember one experience I would probably never forget. I remember reading through the Design Patterns book, several times over, after it came out and a few years after that as well. And I remember reading about one particular pattern as an example, the Memento Pattern. And I really looked at it and said, I don't have a clue why I would use this. And I kind of put it away in the back of my mind. And I remember a few years later, I was working on a piece of code at my office, and I said, wait, this problem really seems like something that could benefit from the Memento pattern, which I've never used before. I've read about it, I've kind of played with it. And immediately I went down searching for the Design Patterns book, looked at it, read through it again, and after several years, it's like, aha, that's really a good example, good situation where I could actually use this pattern. So sometimes it may be a long time before we could use a pattern, so let's not use a pattern into it. It often leads to complexity. That brings up another experience in my mind. I had a developer come to me and said, hey, I'm really trying to use this particular pattern in the code. I'm having a really hard time. Can you help me with it? And I said, I'll be delighted to. Let's talk about the problem you're trying to solve. And the developer explains the problem and what he's trying to really solve. We talk about it for a few minutes. We go down to a little board. We picture a little diagram of what we could do to implement. And we're having a good time talking about the problem. And I said, would this really help you to solve the problem? And the developer said, wow, this is actually quite simple way to solve the problem. I think I'm going to get this implemented in the next 15 minutes. And almost steps out of the door and stops and turns right back and says, but wait a minute, you told me how to solve the problem, but you never told me how to use that particular pattern. And I asked, well, is your objective to solve the problem or to use the pattern? And he kind of looked at me and said, I guess it's to solve the problem, never mind, and walked away. So the point really is sometimes we get really hung up on a particular pattern to solve, and that's like kind of walking around with a hammer asking, can you show me a nail I can hit? That can be a really dangerous situation to be in. So you want to really rethink about it. So having talked about that, let's talk about some patterns we can think about in solutions we can use and how we can benefit from them along the way. And I'm going to be writing some code as we go along, and I will just keep pushing that code into a directory. And towards the very end of this talk, after the talk is over, I will take the next about 5 minutes and zip it up, and I'll push it. It's not there right now. If you go to the link right now, it'll give you an error, but eventually I'll post that into my website, and that's where you can download the examples I post. And again, I'll show this link to you towards the end as well, but that's where it's going to be eventually when I push the code towards the end of the presentation. So with that said, let's talk about optional. Now, one of the key things I keep emphasizing quite often, and I really cringe this quite a bit when I see it, is that I want to really remind ourselves is null is a smell. And we really want to avoid null in code as much as we can. Now, unfortunately, in some data we may process, we may get nulls at some time, and we have to deal with null. But as much as possible, we want to definitely avoid null in the code when we can. But of course, the problem really is we want to really think about a good design. So I want to say a good design, I would say a good design reads like a story and not like a puzzle. So essentially, you want the code, really, the design to be quite obvious. And I really like code that doesn't make me think. That way I can spend my time thinking more important things than how a code should be used. So you really want the code to be pretty direct, pretty obvious. And so, I would say, make the code, obvious. The problem really is when you look at a piece of code, you're not certain what the code is going to do. Is the code going to return a certain value? Do we want to be defensive in calling that particular function? That's not a really good way of writing code. That's not a good way of designing software either. So in that regard, if you remember the sage advice from effective Java, so what did they say? The effective Java said, do not return a null. Instead, it says, for example, return an empty object. So empty list or an empty collection for that matter. So I think that's a really good advice if we follow it. So any opportunity where I'm returning a certain data, if it's a collection, I would rather return an empty collection rather than a null. And of course, the benefit of this is you can iterate over an empty collection. You don't have to perform a null check on it. And that really saves not only a few lines of code, but more important, it doesn't ask you to verify every time if it's a null or not a null. And secondly, of course, sometimes you see programmers that want to, expect null everywhere they turn around. That's not a good way of programming in general. So essentially, if you are returning, let's say, a public, let's say, for example, a list of, names, let's say, string, and I'm going to say get names. And in this particular function, if there are no names, you really want to return a list of empty rather than returning a null. So that's a good practice in general. We can follow it. But the question really is, that's a really good advice for a collection of data. That's wonderful. But what if we don't have a collection? So what if we have a single value? What do we do? That's the question. So obviously, in the past, we returned a null, if you will. But of course, Java has legacy. Java cannot just wake up one morning and change the contracts. A language that's being designed relatively new can introduce some really nice features, but we can't really do that in Java. So what is Java's approach of dealing with this? So in the past, we returned null, but now we should really return, you could say, return an optional, if you will, of whatever it is that could be. Now let's talk a little bit about this because there seems to be a little bit of confusion around how to actually use optional. So I want to focus on the do's and don'ts related to optional as a good design pattern to follow. What should we do? When should we use optional? And when should we not use optional? So let's talk about that a little bit further in here. So for example, let's say I have a little function here, and I'm going to say something along the lines of, let's say string, let's say get name, and maybe in this particular case, there is no name, and so you return a null. So I'm going to just put a bad idea here. This is not a good way of programming. The reason, of course, is the caller doesn't have a clue that the name may not exist. And of course, we are telling them if the name doesn't exist, you better start handling it with a null check. That's not really a great idea. So what should we do in this particular case? So you can say optional of string, and then you could say, instead of this, of course, you could say return optional of empty. That would be a good idea. Now, just as a quick note, by the way, I saw somebody do this actually, and that's why I want to mention this. They had an optional string, and then they still returned a null. There are some people who can never be helped, okay? So just to be sure, that's really, really terrible. I would say, heck no, right? This doesn't make any sense whatsoever. But again, some people you can just stop some people from letting them burn the world. So essentially, that's terrible. But anyway, you want to return an optional of string. And in this case, of course, you want to return an optional empty if the name doesn't exist. So in this particular case, let's play with this a little bit. It's a contrived example, like a lot of examples are. So we'll say math.random, let's say greater than 0.5. We could say in this particular case, return, let's say optional of, let's say in this case, Joe. And otherwise, we're going to return an optional empty, like you see in this particular case. So that's great so far. So let me just change the version of Java here before I go. So essentially, you can see that that's basically the code we just saw is giving us that particular result. So how do we use it? So one way you can think about this is you could say, result is equal to get name. And you want to really get the name out of it, so we can just print the result right now. You can see optional Joe in this particular case, or you can run it and you can eventually see an empty as well that pops up eventually as an optional empty. But how do we get the value out of this particular optional? Well, a couple of things again to think about. So you don't want to say, so why is this better? The reason this is better is if the get name was returning a null, we would have said something like if result is not equal to null, again, that is a smell, you want to keep that in mind. You don't want to be performing that kind of a null check. Well, not only do you perform a null check, more important, we could forget to perform a null check. And if you forget to perform a null check, what could happen? Potentially a null pointer exception at runtime. How many of us enjoy getting a null pointer exception? Not many people. In fact, it can be even more disastrous. If you don't trust me, you got to talk to my friend Brian Sletton. He once posted a tweet, which probably I would say is the scariest tweet ever, because he turns on the TV and the TV displays a null pointer exception. Forget about watching scary movies, right? That itself takes care of it. And so you don't want to do that. So when you see a TV, display a null pointer exception, it's like it's safe to just turn off the TV and take the rest of the day away from it. That's not what you want to do. So how does it really even end up happening? Well, somebody didn't catch the exception. Well, they didn't check for null to begin with. So in other words, the beauty of this approach is, A, you don't have to do a null check, but more important, it forces you to check if the value exists or not. So in other words, it makes the code a lot more safer by turning that potential runtime failure into a compile time failure. That is one of the biggest benefits is anytime, and don't get me wrong, I'm a big fan of testing, but I would rather have the compiler tell me I'm stupid than the runtime unit test tell me I'm stupid. If I'm stupid, I'm going to find out anyway that I'm stupid. I would rather find out sooner than later. So compiler errors are definitely better where we can have them. So as a result in this case, you can say, I want to get the value. Now, having said that, one of the ways you can get this value is you can say output result or else, and you could say, for example, not found, like so as an example. So you could substitute a value for it and say, if it is there, get the value Joe. If it's not there, get me a not found as a response. So you could do one of those ways. So that's a reasonable approach. But I would recommend, please don't do this. And that is to say result.get. Well, the reason get is a bad idea is a get will blow up if the object doesn't exist. And, that's kind of defeats the purpose, isn't it? Because the reason we wrote this is to avoid an accidental null pointer exception. Now we get an accidental no such element exception, which is, I don't know which is scarier, right, to be displayed on the screen. So I don't think that's really a good idea, so don't do it. And so I would really prefer if the get method did not even exist. But you say, well, you know what, I really want to get the value out of it. I don't want to give a substitute value. How do I really, do it better? So the problem with the get is, get does not reveal its intention. So this is again, from the design point of view, you want code always to really specify its intentions very clearly. This is one of the things, honestly, I struggle when I write code, is to always ask the question, does the code convey the intention very clearly? Because if a code conveys the intention really clearly, you're removing the surprise for the programmers, you're minimizing the cost of development as well. And the problem with get is it doesn't reveal the intention. So what would a better name for get be in general? They should have really called a get as, will blow up if not present, right? That would have been a very clear intention. In fact, they actually gave that name, but more concisely than that, they said or throw, which is a lot better. And guess what or throw is? It just get. But it tells you, you dare not call me. So that's why I like that name much better than the get. So if at all you need to use get, then use or throw instead. So that's a much better way of calling the function rather than calling it or throws. I can't remember the actual function name. So you can look at the API for finding what the particular call is, and that would be the function to use in general. You can figure out what the method is and use that equivalent. I'm running out of that from my mind at the moment. So essentially the idea is you want to really use the optional. So question is, when should we use optional? So a few recommendations. So first thing to keep in mind is, if a method will always have a single value as a result, please do not use optional. So don't use optional if the value will exist. So if the value will always be there, there's no point in using optional. You want to make it very clear, if you call this function, you will get a value, no doubt at all. Secondly, if a method may or may not, so may not have a single value as a result, then use optional. Of course, if the result is a collection, then don't use optional. Another thing, right? Because if it's a collection, you can already return an empty. Don't put an optional collection. That doesn't really make any sense. But of course, one important aspect we want to talk about is, what about this idea where, let's say, you want to write a function, and what you're trying to do here is, you're going to say set something, and maybe a set name maybe. And you want to say if a name may or may not exist. So you say, in this case, string name, and maybe the programmer had written code like this in the past. So, well, let's say this is a legacy code, and they just wrote the code like this. So legacy code, something like this. So they say if name is equal to null. Again, that is a smell. You don't want to really write code like this, but you probably see something like that in the legacy code. So then they say, in this case, maybe in this case, a name is equal to maybe, this dot name or whatever, right? So use default value of, let's say, value of Joe, maybe in this case. And otherwise, you're going to say use the given name. So essentially, that would be really a terrible code to write, but maybe we did. But we want to really change this code moving forward. So, a temptation maybe, right? Tempting but don't. So don't do the following. Don't say public static void set name optional of string name. This is terrible, by the way. And of course, in this case, you could say if name dot is present, you could say, use the name. So you could say use the given name. Otherwise, you could say, else maybe in this particular case, you could say, use the, default value Joe. But why is this such a bad idea? one of the key things about design is a good design has empathy. So you want to really have empathy for the poor programmer who is using your code. You want to ask the question, when they are looking at the code, are they going to smile or are they going to curse? And that is something we need to really ask the question. And in this case, it's mostly going to be a curse. And the reason is, how would somebody use this code in this particular case? The problem here is they're going to say set name optional.empty if they want to really use a default, or set name and they're going to say optional dot, let's say off, let's say Sarah. Well, in this case, they are being punished every single time they have to call this function. And there's no better way to think about it as a punishment, right? Because every time they got to wrap things in an optional, it is not going to be a fun experience using this particular code. It is really not a fluent piece of code to write. So what should we really do? Well, think about the empathy, right? How do they feel using this particular code? So what you really want to do is the following. You want to take this particular code and you want to simply say, hey, if that is really important to provide this particular way of setting the code, let's do a set name and don't provide any arguments. And in this particular case, of course, you're going to say use the default value Joe when they don't provide any argument. And you can then say public static void, and you can say set name string name. And of course, in this case, you can say use the given name for whatever you're going to do. So that would be a better piece of code. So why is this better? Again, from the user point of view, they can simply do a set name if they don't care to give a name, and set name Sarah if they want to send a name to it. That becomes a lot easier to use it. So the moral of the story is, do not. So in general, don't use optional t as a parameter to methods. So that's generally of no use, if needed. So if needed, use overloading instead of doing this becomes a lot more fluent way to write the code. So that's again a practice we want to avoid as much as we can, is don't be tempted to pass optional as a parameter because it becomes really hard for users of the code. Think of the empathy from that point of view. And then finally, of course, there is a little reason to use optional as a field as well, because that's purely encapsulated within your object. It's not about others using the code. Again, keep in mind, the reason is to make sure we don't inadvertently end up with a runtime exception. Well, in this case, we can safeguard our own code within our class. Very little reason to really use optional as a field within a class. So generally speaking, I would say those are the recommendations you want to follow when it comes to optional. So return optional only when your object may or may not exist, and don't use it as a parameter anytime soon. In general, I would also say if some developers have this habit of checking null on every single parameter they receive. That design pattern is called being a paranoid, and doesn't really help, right? We shouldn't be that scared in the code. So we got to say, hey, you need to really send me the data. Don't send me a null. That becomes a much better practice in general in terms of how we write the code. So that's what I would recommend in general. So I'm going to put this away, save it away as optional, and I will go ahead and save this away so you can you download the code later on if you're interested. So use of optional, and I'll just save that away into here. And so eventually I'll zip it and push it onto the site, and you should be able to see it. So that's basically a recommendation around optional, when to use it, when not to use it, some patterns and some anti-patterns in there as well for us to think about. So that takes us to the next topic I want to talk about here is this concept of iterator patterns. Iterator patterns obviously changed quite a bit thanks to the functional programming APIs in Java. And I think we should really embrace that a lot more. But again, there are a few patterns and anti-patterns I want to really emphasize when it comes to Iterator Pattern. And the reason I want to really emphasize the anti-patterns is, we are out into a few years since we have all these things. I do a lot of code reviews for my clients, and almost any time I do a code review, I find that these are consistent problems because programmers often don't think about the consequences of these when they're writing code, and if they don't have a significant code review in practice, these code can be lingering around for a long time, and we may not even know the problems until a while. So I'll talk a little bit about the anti-patterns here as well as we go along. So let's talk about the next one here. I want to talk about the Iterator pattern here. So let's talk about that. So this is going to be on the iterator. And so in the iterator, let's talk about, once again, where does this come in? So in the past, what we had was external iterators. So external iterators basically where we control the iteration every step of the way. So essentially, we have to write all the code ourselves. Let's talk a little example here. Let's say names equal to, let's say list of, let's say some names will start with right here. So given these names that we are interested in, what if I want to iterate through these names and I want to, print maybe the names of the people who are, have a name of 5 letters long, but I want to print it in uppercase? Well, we could do something like this. We could say for int I equal to 0, which is really a very verbose syntax as we know, and less than or equal to names dot, a size or length, whatever. But that's really a very verbose. Thankfully, we don't have to do that. But this is still an external iterator. You could say, for example, name coming from names, and you could say if the name, let's say dot length is equal to, let's say, a 5, you could simply output right here something along the lines of name dot to uppercase, and you could print out the name all in uppercase. So that's an external iterator where we controlled, and typically you're going to have things like a break or a continue or parts of these as well, depending on what we are trying to do. So we are trying to really alter the flow of iteration in the code when we do this. But having said this though, in this particular case, we could, instead of doing all that extra effort, we could simply do it this way. We could say names.stream, and then of course we can do a filter, and given a name, we could say name.length is equal to 5, and we can map this to a toString obviously in here. And then finally we could say in here for each, and a system.out and a print line, and we could simply print it. So that becomes a nice functional pipeline where we can just flow through and be able to implement the code very easily. So this, of course, is called the internal iterator. So internal iterator, because we are not in the business of controlling the flow of iteration, but instead we are focused on simply saying what we want to achieve for the elements, and the iteration is taken care for us behind the scenes. We don't have to really do this. So this is pretty nice if you think about it. But when you look at this particular code, you see that it flows through nicely and gets us all the data. But let's say in this particular case, rather than a value of 5, I want to say a value of, let's say, 4 for this particular example. And you can see in this particular case, we have 3 values we printed. To make things a bit more interesting and worse for the imperative style, you might do something like this. A count is equal to 0, and then you may say something along the lines of, if count, well, first of all, you want to increase the count right there. And you say if the count is less than, or equal to 2, and then you can say in this case a break, because I don't want more than 2 values. And you can see Dory and Gil being printed. Well, that's break that we are writing right there. So the question is, how do we really break out of this? Well, it turns out in functional programming, we don't have a break statement. In fact, that's exactly why, because a break is a statement, whereas in functional programming, we don't have statements, we have expressions. So the question is, how do we really deal with it? Well, thankfully, that has been introduced in Java 9, much later than Java 8. So what you can do here is you can say, you can say a take while. For example, if you want to base it on maybe the number of elements you want to really look at. So, pardon me, the value of the elements you want to look at. So you could say a predicate could be coming in. So there's a much more flexible break available if you really want to go beyond the count. But in Java 8 itself, we have a limit of 2, which can be really useful as well, and that can control the elements we are seeing. So limit and take while really are the break equivalent in functional programming. That is something we can keep in our mind. So we can say limit and take while are the functional equivalent of break in the from the imperative style. So you could say from the imperative style. So essentially, you could say these are really a nice way to structure the code. So that's an example of how you can do iterations in the functional style. So we could say internal iterators. So this is a much better way of writing code. And in general, I would argue this is what I prefer writing these days as much as I can, is to use a functional style where that's possible. But having said that, we got to be a bit careful about this. And if you're not very careful, things can be a bit of a surprise. So for example, let's think about a functional style code, imperative style code first, then a functional style code. So I'm going to say, in this case, let's say result 1 is equal to, we'll say new array list, and let's start with an empty array list of string to begin with. And I want to print the result of this in the very end. So what I'm going to do here is to say, comes a name coming from the names collection. And all I'm going to do is to say, if the name of length is equal to 4, I want to simply say result 1 dot add name dot, let's say, to uppercase, and convert this to uppercase and add to this particular collection. We have Dory, Gil, and Nemo in the output. But how would we write this code more in the functional style in here? So you could start out by saying, for example, a list of, let's say, a result in this case. So result 1, you could say result 2 is equal to a new array list, and you could say string, and you could then be tempted to do something like names dot stream, and you could do a filter name, and you could say name dot length is equal to 4, and then you could say dot map string to uppercase. And if you stop right there, everything is going great. But unfortunately, though, I've seen many programmers do the following. They would do a for each, and then they would say something along the lines of name, and then result2 dot add name, and add the name, and I'm going to say bad idea. So just want to put that in there before I go further. And then, of course, you can go back to this particular code, and you could try providing, in this particular case, maybe let's output right here a result 2 in here. But when you run the code, you can see Dory, Gil, and Nemo. Now, I say this is a bad idea, and a lot of programmers have written code like this, where in the functional pipeline, they are modifying a collection that is given. But I'll share with you one story. This was a story. I got an email one morning, and this was a programmer who was working for, let me just say, be vague about it, for a financial company. And they are dealing with millions and millions of investors who invest money into this particular financial company. That's the maximum I can tell you about this. And the email he wrote to me said, hey, Venkat, I need your help. If you can quickly take a look at this code, it worked great until yesterday. And this morning, it doesn't work. Can you please look at it for me? I didn't have to spend a lot of time. The minute I read, it worked yesterday, doesn't work today, I immediately jumped over to the code and I saw what this person was doing. And this was not names, obviously. These were funds, investments, and the programmer wanted to treat certain types of investments, perform some operations on it, and put them back into a collection. So this was a collection of investments that underwent the transformation, and I saw that code. And of course, he didn't have the bad idea comment in there that would have been helpful, but I saw that code. And I'm looking at that, I'm saying, so he is mutating the data. And immediately my eyes jump over here, and the code here said a parallel stream. So now you know what happened between the yesterday and today, right? Well, the developer had the code with the stream all along, and that morning put a parallel stream on it to make it really faster. And the whole hell broke loose after that. The problem really is the code runs, and unfortunately, it didn't produce the right results. So I quit saying, these days, I don't say code works, because that's a tall order. I often, now say the code, I could say the code behaves, right? That's all you can say, right? The code does something. And does it do what you want to do? It depends, right? So it really is unpredictable. So what is wrong with this code? This is one of the biggest dangers of writing the functional style code. So the problem in this code is the functional pipeline is not pure. So essentially, we are doing shared mutability. So this is one of the things, again, as an anti-pattern, is something we need to really avoid, because this can be very dangerous. So we're doing shared mutability, and it's okay to perform mutability. You think of mutability as changing clothes. It's okay to change your clothes. Never do it in public, right? That's a way to think about it. You want to really do it in private, so you can change your variables, but not in a way it can be seen outside. So shared mutability is a terrible idea. And the reason I want to emphasize this is I see programmers do this over and over and over. And in all honesty, I'll be absolutely blunt and frank and honest about it. There was one morning I opened a piece of code only I was working on, and I saw me do this also. And I was in a state of shock. And the only thing I can maybe think of is I did leave the code open on my computer. Maybe aliens came and changed it when I was away, right? Because I would never do this, definitely, but somehow that happened. Well, it's natural for us to make this mistake. So this is something we need to constantly be looking back at the code and asking, are we performing a change to the code anywhere? So the functional pipeline is not pure. We are doing shared mutability. So the problem is the result may be unpredictable if we ever change this code. So change this code to run in parallel, by adding dot parallel, right? Dot parallel, or by changing, in this case, dot stream, in this case to dot parallel stream. Now, I was discussing this a few days ago, and a developer said, yeah, but this code is not running parallel. My argument is nobody said it shouldn't ever be run in parallel. So unless you can clearly prevent this code from ever running in parallel, you cannot really risk that. That is extremely difficult. Well, in fact, I would say this developer who reported the problem to me was extremely lucky, because as you know, if you are very lucky, the code fails on your machine. If you're not very lucky, it waits for the production to fail. So this was really fortunate that it actually failed on his machine, and that maybe is a new slogan we want to write. It fails on my machine, right? Rather than it works on my machine. I would rather it fail on my machine than fail in production. That's the problem with the code like this. So the moral of the story is, a functional, you could say a functional pipeline offers, you could say, internal iterators, you could say is less complex, easy to modify, easy to, understand, but you want to put that very big emphasis, but it is very important that we make the functional pipeline pure, avoid shared mutable variables. So this is extremely important as much as we can. Of course, as you know, in this particular example, this is relatively easy to do, but I've actually seen even worse piece of code. So in this particular code, obviously, what you could potentially do is, rather than going through and modifying the result in the last step as we did, you could have said .toList, and you could have gotten the list out of it really nicely. That is a better option, rather than mutating. But like I said, I've seen much worse code. For example, I've seen developers do a map, and they take a particular object, and then they go do perform, mutable, impure operation right there. This is really a bad idea. So you want to avoid that, right? So avoid these kinds of code as well. It can be really dangerous. So this is where I think it's important to really examine the functional style code. And like I said, I do quite a bit of code reviews for my clients. And when I do, I can't tell you how many times I flag these things and say, oops, we shouldn't do this. Oops, we shouldn't do this. And we should really make the code pure. A lot of times I would say these are ticking time bombs in the code. You don't know when it's going to blow up, and it's also unpredictable. You could run the code for a long time and never see an error until one day it blows up in production. And even worse, you cannot repeat it so easily. So if you call a colleague and say, look, the code fails, the first thing they're going to ask you is run it again, and now it doesn't fail. It can be really frustrating to see these problems as well. So that's a very common anti-pattern. We want to avoid it. So the moral of the story is absolutely make sure that you have the functional pipeline has to be extremely pure. Now, from the point of view of purity, I want to go a little deeper into it. So what is a pure function? And I'm going to say two things about a pure function, and you're going to say the first one is obvious because everybody knows it. But I cannot tell you how many times the second one is something we probably have not thought about so far, and it's really important to think about the second rule as well. Now, of course, what is a pure function? A pure function, you could say, is idempotent, and it returns the same result for the same input, right? Input, and does not have any you could say side effects. So this is basically what a pure function is. But the two rules of purity are extremely important to keep in mind, and both the rules are absolutely necessary. The first is it does not change any state that is visible outside. So I would say, duh, that's obvious, right? So everybody is going to say, of course, Venkat, if it's immutability, if it's no side effect, it shouldn't mutate anything, it's obvious. But the second rule, a lot of people don't think about, but is as important, if you will, if not more important. And that is, it does not depend on anything anything outside that may possibly change. So the second rule is actually as important. And a lot of times we tend to forget it or ignore it, and that can be a disaster in the making. So it does not depend on anything outside that may possibly change. The reason is, if your pipeline is executing right now, and while you're in the middle of your pipeline, if that variable can possibly change outside, an external agent, another thread potentially, for example, might modify the data, and your pipeline's behavior is no longer the same. So in other words, it's really important to understand, I'm a big why kind of a person, right? I can be very annoying asking why, but why, but why, but why. So I want to really emphasize that functional programming relies on lazy evaluation for efficiency. And you want to emphasize that lazy evaluation and the parallel execution rely on immutability and purity of functions for correctness. So essentially, this is the reason why we need to really emphasize it. So FP emphasizes, you can say, immutability and purity, not because it is fashionable. So it's not so they can look different or cool, but because it is essential to its survival. So you will not be using functional programming if you don't have efficiency. You wouldn't be using functional programming if it doesn't offer the benefits. So really this comes down to survival. Functional programming wouldn't exist meaningfully if we cannot provide efficiency. Because if you build a pipeline, and in the pipeline, if you're going to be transforming data into new collection after collection after collection, guess what's going to happen? That's not going to result in a good performance. It's going to become really slow. You may have a lot more garbage to collect. And in cases where you have a large amount of data and you don't care to process all the data, you would be performing all that computations unnecessarily. Well, functional programming smartly avoids that by using lazy evaluation. Well, but laziness cannot be correct in the presence of impurity and mutability. So this really is a fundamental. So a lot of times when we get into functional programming, we are told you should not mutate variables. That's like telling children they should eat vegetable, right? It doesn't go very well. But instead, if we really ask the question, but why? Why should I really honor immutability? Well, because if we don't, our program execution is completely messed up. It's not going to give us the right results, like this person who wrote me the email to say, oops, the code worked fine until yesterday. It doesn't work well anymore. Well, why does that really mess up? How did this end up being really wrong? Well, the code ran into a race condition at that point and gave a wrong result. That is something we need to be very careful about in terms of how we are going to think about. So the purity is extremely important to consider when it comes to these kinds of code, because it can be really treacherous if we are not careful about. So I'm going to say purity and internal iterators, this is one of the biggest risk, I would say, that we run into. And again, like I said, I've seen a lot of code where developers don't pay attention to this, and you look at this pipeline, and it's even more disastrous because they may not perform a mutation right at the at the lambda that you see, but the mutation may be happening within a function deep down, and that could be a problem as well. So we got to be very careful about this too, and we want to be making sure these functions are really pure. That becomes absolutely necessary. So that's about being careful about iterations. Again, a few patterns and anti-patterns to think about when it comes to how we build these iterators and how we use them can be a really powerful mechanism to consider. So having said this, let's move on to the next one. We all have used the strategy pattern at some point in our work. So let's think about the strategy pattern. So let's think about the strategy pattern as we know it from the past. So what is the strategy pattern? So essentially the strategy pattern is where we want to vary a small part of an algorithm, you could say, while keeping the rest of the algorithm the same. So that's basically where we use a strategy pattern. So we want to be able to modify or vary a small part of an algorithm, but we want to keep the rest of the things really the same. Now, unfortunately, though, this is a very powerful pattern, very interesting pattern. However, language design is program design. This is where it becomes very tricky. Languages influence our design. We cannot design in isolation of the languages. When a language restricts what we can do, we end up a bit powerless. In fact, this is one of the themes that I want to really emphasize is, design patterns often kick in to fill the gaps of programming language. So in other words, if we celebrate design patterns a lot more, that's not a good sign, because design patterns are really to fill the gap where a language actually ends up failing, if you will, or at least not being up to the par. So a more powerful, I would say, a more powerful language is, you could say, the less we talk about design patterns, as these you could say naturally become the features, if you will, of the language. So essentially, if you really are working with a very powerful language, you would need fewer patterns. If you're working with a language that's not as powerful, you tend to really compensate for it with patterns. That's a nice way to think about, right? Patterns there often compensate for where a language doesn't step in and fill in. It becomes really nice. You don't say inheritance pattern, right? Why? Because inheritance is a natural feature in languages, most languages that do object-oriented programming. So we don't talk about them as patterns. They just become practices, if you will. So that is something to really keep in mind in general. So in the days of the past, right? So in the past, how did we use a strategy? So essentially, when you wanted to use strategy, what did you do? We created oftentimes an interface, right? So you create an interface and then a bunch, if you will, of classes. Then wire them together, and often you say using factories. And so if you wanted to use a strategy pattern, it was quite an effort. So here is how you did the strategy pattern oftentimes, isn't it? If you want to use a strategy pattern, you would organize a design meeting, isn't it? Because you want to make sure you want to invest this time doing this. And by the time you discuss this, you forgot why you wanted to do it in the first place. That's a lot of effort you had to put in to bring in the strategy. Well, thankfully, we don't have to do it. So you could say lambdas are, you could say lightweight, you could say strategies in general. And you could use lambdas as a nice way of bringing strategies in place that can help us to design the code a lot more effectively. So let's think about this, and we'll put a little code together here. We'll say strategy and see how we can use the strategy pattern here as well in this particular example. So let's start with a little example and play with it, and nothing really complicated, and then see how we can maybe grow this into a little bit of a pattern, if you will. Now, remember, it's also good to write minimum code to make things work. So maybe a requirement given to you was the following. So we'll start with this as an initial code, if you will, and then we will grow into it. Actually, I want to really save that little notes here as well for you. So give me a second to put that together. I don't want to forget bringing that in. Let me make sure I bring that in. So this is going to be on the strategy, right? So on strategy. So essentially, how do we really approach this? That's what I want to start with. So, suppose, let's start with a little problem here. So suppose, we have, a collection of numbers, right? Maybe, price of, stocks, you could be products, etc., whatever it could be. And we, let's say, are asked to write a method to total all the values. So very simple code, nothing really exciting. So we want to total all the values. So how do we go about doing that? So let's start with a little example. We'll say numbers is equal to, and we'll say list of, let's say list of numbers 1 to 10. We'll start with that little list and go forward. So given these list of numbers, what I want to do is to say output, we'll say total values, right? So very little innocent code, nothing really exciting. So we'll say numbers and we will simply print it. So where's the total values? So let's start with a little example of total values. Let's say here comes a list of integer, we'll say numbers, and here comes the little imperative style code. So we'll say total is equal to 0. We'll refactor this into a functional style a little later on. So I want to return a total value in the very end of this as well. But what are we going to do to loop through this value in here? Let's say for, let's say in this case a number, and the number itself comes from the numbers collection, and we'll simply do a very simple total plus equal to, and we'll simply say the number that's given to us. So a very simple piece of code. The result is a 55. So this is an initial code. We'll just save it away, initial code. Maybe you are really having a, maybe think about this as a Friday evening. You really are excited to go to this, event. You're going to meet a very, long lost friends. You've been eagerly thinking about it, talking about it for weeks, and you're about to leave when your colleague, you know who I'm talking about, right? The one who annoys you with all the requests says, hey, I want one more function. I want to total not just the values, but I want to total the even values. And you say, is that what you want? You want to just total the even values. And your colleague says, yep, I want a function to total the even values. And you're not in a mood to write this code, but you're thinking, how do I get this done really quickly? I want to really go to this event. And you're thinking, you know what? Most of the code already exists. And I don't have to write a lot of code. And then you tell yourselves, there's got to be a reason why they created copy and paste, right? I mean, if nobody should ever use it, why would there be a copy and paste, right? So there's got to be somebody to use it. So you gently copy it. And in fact, it's such a beautiful feature. They even give you shortcut keys, a control C to copy it. How cool that is. And a control V to paste it, isn't it? So you can just do a copy and paste of that. And then you simply say total, even values. And then you come down to this code and say, if you could simply say a number mod 2 is equal to 0, then total the value. Otherwise, don't total it. So you could write that code and you could simply push that in. So this is, of course, one change we included. But as the fate may have it, before you could leave, your colleague says, I want one more change from you. I want total of odd values as well. And now you're thinking, oh my goodness, what do I do right now? And you realize this time you want to total the odd values in this collection. And if you copy and paste it right now, what's going to happen? Well, if you copy and paste it this time, you're going to have a duplicated code a third time over. Now, we all can agree that copying and pasting a code a third time is an act of criminal negligence. And that shouldn't be done, but it's Friday evening, nobody is looking, so you might be tempted to go ahead and push that in and walk away, right? So this becomes a yet another change. But here is the problem. You then start driving down to this event, and as you are driving down, the guilt eventually kicks in because you didn't really sign up to write such code, isn't it? So you pull up by the nearest coffee shop and you want to get the guilt over, you start refactoring code. But as fate may have it, some of your other friends are hanging around. They come around and ask you what you're doing, and before you could close your laptop, they take a glimpse of your code. And they find out that you do copy and pasting for a living, right? That's the last time they ever return your messages. They don't want to meet with you anymore. Life becomes dark after that, isn't it? So we definitely don't want to be writing code like that. That's terrible code, and we don't want to be duplicating code. So let's pretend this never happened. So what we do is we'll reverse out of the change. We'll go back to what we wrote. Hey, simple code that works is all great. So we just wrote that code right there for the values as we wrote, and that code actually works. But now the requirement is your colleague says, I want to total all the even values as well. And you ask the question, hey, do you want both of those implementation? And the answer is yes. Well, that's a great time for a little refactoring before we move forward. So essentially, we go back to this code and we do a little bit of a refactoring, and we fall back and refactor to the original code. So we'll just fall back to the code right there. So we'll say fall back to original code, and we'll just say save it away again. So now that we fell back to it, what do? A bit of a refactoring is in place. So we can come down to this code and say comma, and we can now say, hey, I want to bring in a strategy in this place. Well, lambdas are a great way to do strategies. And so let's step back for a minute before we try that. So one of the key things is strategies, if you will, a strategy are often a single method or function. So essentially, strategies often are single method or single functions. Now, sometimes we go on the wrong direction, not because of an intent, but because of the environmental consequences. Remember the time when the Design Patterns book came out and a lot of these ideas were being promoted. The famous languages of the time was C++. C++ did not have lambdas back then. Then when Java came out, Java had the ideology of being object-oriented. And unfortunately, though, when Java introduced anonymous inner classes, that was a missed opportunity as well. Because if they had introduced lambdas instead of anonymous inner classes, we have gone in a different direction 20 years ago. But in this case, the ideology of object-oriented programming was pushed a lot further, and we refused to think about functions as first-class citizens. So the route we took was to really build classes that were wrapped around functions. So as unfortunately, though, we were treating functions like they are kindergarteners. This little child comes to you and says, can I go to the park, please? You say, no, sweetie, you cannot go alone. Let me send an adult with you. So we wrap this function into objects and push the objects around for no good reason. So that didn't really help us. So strategies are often a single method or a function. So you could argue in this case, so a functional, in general, a functional interfaces and lambdas work really well for them. So this is one of the reasons why this is a perfect match, if you will, for using a strategy pattern. Is lambdas fit in really well to strategies in general. So you can say in this case, I want to take a predicate, and in this case of a predicate of integer, and we could say selector, and you could pass an int predicate as well if you really wanted to. That's perfectly fine. So we have a predicate of integer selector. Then we simply come in here and say, if the selector dot test of number is true, then perform the total, not otherwise. So we are simply introducing a strategy, and that functional interface predicate simply became the strategy in this particular case. So going back here, we could then say a comma, and we could say, given a number, I'm going to simply return a true. And you could use a ignore. By the way, I'm hoping that eventually, sometime in the future, we can use an underscore for that purpose, right? We not there yet. Underscore is the international symbol for I don't care, but we don't have that yet available for us for our use. So I generally tend to put ignore. I like ignore rather than the famous X people put. I don't know where that came from, but I want to be descriptive oftentimes. So I could say ignore that and return that particular value in this particular case. So we could say in here comes the value that we are interested in. So what am I going to do with this particular code? So let's go ahead and bring in let me try this again. So we're going to go back and bring in the function dot predicate, which is what we are using right now in here. So let's go ahead and bring that in. So now we have a total values, and then of course I'm going to say in this case a comma and ignore and return a true, which is the value I want to return from this particular call, and you can see that that works. So we just did a little refactoring. That's what we did to bring in the functional style and the strategy into the mix. So now that we have the strategy in here, what we can do now is to say, well, here comes a total, we could say even values. And for this, of course, we could say here comes the number, and we could take the number given right there. And we could say, for example, a number mod 2 is equal to 0, and we could bring that in to total, all the even numbers in this case. So this is obviously total values, not total even numbers. We can just bring that in and use that. So that becomes our second function we can use. And just to emphasize this, to make it a little bit more cleaner, we could also have a Boolean, let's say, is odd, and we take a number in here, and we could have said something along the lines of return number mod 2 is not equal to 0. And if you want to total the odd numbers, you could simply take this total values again, but this time you could simply say take a number. Well, instead we could simply say this becomes a sample, which is the class where we are, is odd, and we can simply pass the is odd function to it as well to make it a lot more concise. So we could potentially do that as well right in there, as we can see. So that becomes a nice way for us to use the strategy in here and be able to represent the data in a very cohesive way. And the code becomes a lot more simpler to write as well. And we're not sitting there and fighting the environment to write the code, and instead we can simply make it very expressive. And of course, this is using the strategy. And of course, one more change to really bring this into a functional fold. So we can then say, finally, one more little refactoring. We could say this becomes a return. We could take the numbers dot, that's a collection, so we can do a stream on it, and then we can do a filter on it, and then we can pass a selector to it, like so. And then we can then say in this particular case, well, if at all, we could simply say, well, a map to int given an element. Well, in this case, I'm just bringing in a sum function in there, but you can also get an int stream right off the bat here, and then you don't have to convert to a map to int in this case, and then you can use it and further refactoring as well you could potentially do. So you can convert to an imperative style to a functional style, but that comes in as a internal to the function. Irrespective of that, you can still use a strategy if you want to, a bit more refactoring for the function itself you could potentially do. So the essence here is it really helps to think of functional interfaces as a strategy. So if we think of a functional interface as strategy, then we are able to make use of the strategy pattern more effectively, where we say, I'm streamlining most of these functions in this particular case, but a little bit of that I want to vary, and I can take them out as a strategy and provide it. This becomes very effective in terms of building our own classes and interfaces. So you could build your own class and say, within my class, I want to write this function, and within my function, I want to be able to receive the strategy and then take, execute as part of it and return back a response. And your strategy becomes a lot easier to build rather than having to put a lot of effort to bring in all the classes and the inheritance hierarchies, and the factories that come with it go away. So typically what I also tend to do is I tend to create a class with a bunch of utility functions that provide the strategies, so I can just simply refer to them in here. So for example, just as a quick note here, you could do something like, for example, you could say, your collection of functions, right? So you could say, let's call it as a business, logic, and then you could specify some, strategy. So you could bring in a strategy effectively like so, and becomes very nice way for you to pull in strategies into the code, because strategies are stateless. That's something important to keep in mind. Well, of course, that brings back to purity of functions in Lambda expressions, right? Lambdas are pure, so they don't have state, so that becomes a lot easier to pull them as a static method and then pull them in. Or it could be part of an object as well. If it has to refer to some data, that's fine as well. You can bring them into as a method reference to an instance method as well. If that were to make sense, you could definitely do that also. So that brings us to a few more of the patterns we want to talk about. So we talked about a number of these patterns so far, and when you look at the patterns in general, patterns tend to evolve as time goes on. So there are, I would say, three kinds of ways in which I look at patterns. The first is there are certain patterns that we probably don't want to use moving forward, because Java has evolved substantially. We don't need to really use those patterns, at least not the same way. So I would say strategy becomes a feature rather than standing out so separately. You're not putting effort to create interfaces and classes anymore, so that becomes a lot easier to build. The second thing is you may still use some patterns, but they may change the way you do them, become lightweight thanks to lambdas. But I'm also going to talk a little bit about patterns that we may not have used before, but we can use now thanks to the power of the language that we have right now. And this is where certain things we've never experienced in writing code in Java, now we can start using some of these techniques that can be a really powerful way to write the code. This is also one of the reasons why I'm a big fan of learning multiple languages, because when we learn multiple languages, we are able to apply some of these ideas in languages that we use, especially when those languages are changing. We can quickly bring these ideas when we are familiar with. This is something I remember from an experience. I was actually working on a project not far from here for a client, and I was pairing with a developer one day, and as we were writing code, I said to the developer, hey, I've got an idea. Would you mind if I try something a little different on this piece of code? And the developer said, I'm curious what you're going to show, let's try. And so the tests were passing, but we wanted to refactor the code. So we modified the code to a different look. And he looked at the code and said, I've never seen code being written like this before. And as I was saying it, the project leader, who was fairly technical, came in and looked at it and said, hey, are you trying to write Ruby code here in this language? And I winked at him and said, what do you think? And he said, that's pretty cool. Well, I knew that you can do this in Ruby, and it's a question of saying, hey, how can I apply this in other languages? So this can give us possibilities or design tools we may have never experienced before. But with that said, let me switch gears really quickly and think about something else that's kind of a little funny and a little scary at the same time. So I'm going to say one of the key features we are really interested in languages, object-oriented languages, is polymorphism. So what does polymorphism say? Polymorphism really says, go ahead and call a method, but the method that is executed is not based on the type you think at compile time, but the actual type at runtime. So polymorphism has a bearing on extensibility in general. So if you want to make the code more extensible, you often rely on abstraction and polymorphism. So with that said, what is the worst keyword in Java that from the, let's say, polymorphism point of view? So something that makes the code less polymorphic. Anyone wants to take a wild guess? Well, yeah, fire away.
Final.
Final is a good answer so far. I want something to top that. Instance of. Yeah, that one's kind of is bad. But something even more evil. Static. Well, okay, think of all these as little minions. They're all standing there, but on the top of the hill, like way up there, smoking cigar is an evil-looking, really mad keyword. What was that? That's right. New is the mafia of all of them. At the very top is new, and its evil face. And new is so evil, you have many patterns to fight it. But guess what? A new is still smoking cigar and says, keep coming, you morons. And then what? We have spring, right? And spring is like, let me put up a battle. We got Jews, and we have so many techniques, and new is the worst of all. Why? Because new says, I want an object of that specific class, right? So that is tight coupling. New is the worst of the kind. And keep in mind, new is not polymorphic in Java or C# or C++, but new is polymorphic in Ruby, for example. So if you're writing code in Ruby, you can have polymorphism very easily. But of course, there are some languages that are so scared of new, they completely avoided it. There's no new in Python, there's no new in Kotlin, right? They're like, oops, never mind, we don't even want that. So there are languages that deal with it really well, there's languages that ran away from it, and there are languages that are a disaster with new. So something to really think about when it comes to how we can handle it. It's a good time for a 20-minute break. When we come back from the break, we'll start with new and move forward to a few more patterns. So I'll see you in about 20 minutes. Thank you. All right, let's get moving forward. Hope that was a good break. Hope you had a chance to refill your liquids, use the facilities. So let's get moving forward. We're going to talk a bit about a few more patterns here. A few of them influenced by lambdas, and then we'll switch away from lambdas towards the end and look at something a little bit more recent as well. So the next thing I want to talk about here, we talked about the new before the break, and new being a tight coupling. So oftentimes when we use new, you are saying new class name, and that's really a tight coupling that you often have in languages like Java. On the other hand, languages like Ruby, you can specify things like a class name dot new in order to create an object, and you can be polymorphic about the new, and you can pretty much create an object given any class. But of course, in the case of Java, as you know, you could use the reflection API to create an object. Well, that's a bit of a roundabout, if you will. And then, of course, the consequence of that is the minute you do it, you got to deal with all those exceptions that you have to deal with, which you don't have to when you're simply using a new directly. So that's a bit of a mess in there in that case to deal with. But in any case, an entire slew of design patterns have been introduced just to deal with new, to make it easier to make the code extensible in terms of creating objects. But I'm going to touch on one small aspect in here, which is really this use of the factory method pattern and how we can use default methods for it. So when default methods were introduced in Java, I was intrigued by default methods, but at the same time, I was kind of curious to ask the question, how do I use default methods when it comes to classes? Do I use abstract classes? Do I still use interfaces? And in general, though, the golden rule that interfaces are better than abstract classes still holds true. However, as you know, interfaces can have implementations, but they cannot have non-final fields. So in other words, interfaces cannot carry state, whereas abstract classes can carry state. But in that regard, they actually promote a better extensibility quite a bit. But this is where, if they cannot have state, then how do we do something really meaningful with them? Well, this is where a thought about factory method can help us when it comes to designing with the default methods and interfaces. So let's entertain a thought here how we could actually do this. So let's say we have an interface, I want to call it as a person interface, and a person interface, simply put, is going to have a default method, and let's say the default method is going to be called as play, where the person is going to play, and we could call a play method on it. So in this case, of course, I could also say we have maybe an interface or a class, an abstract class called pet. And a pet could be one of different types, let's say, we want to use. And then, of course, we could say we have a class called dog, which implements, let's say, the pet interface. And we could also potentially have a cat, which implements a pet interface as well. So now, of course, when it comes to the play method, we could say something along the lines of, playing with, and we could provide a playing with implementation just to print that message. And what are we going to play with? I'll keep it extremely simple in this particular case. Let's say a pet. But we cannot really do the following, right? We cannot say private pet, and we cannot put the pet within an interface. If this were an abstract base class, we can put a field inside the abstract base class that would work really well. But interfaces cannot have private fields in them. That wouldn't work. So if I try to do something like this, it says expected and gives me an error right there. You're not allowed to provide a pet. So what do? Well, the interesting part about the interfaces in this case is you could simply say a pet, and you could simply say a getPet method defined within the interface like so, and then you could say getPet like so. So this simply says you can have a method. So in other words, rather than having a field within an interface, which you cannot, you instead have an abstract method that will return the field from the implementation that you may choose to use. So as an example, let's say in this case we have a class called, we will say this is going to be a dog person, let's say, which implements, let's say in this case, the person interface. And I can simply say a public pet, and we can do a get pet, and we can simply return, let's say in this case, a new dog, or we can store a dog as a private dog. Let's say a dog is equal to new dog, and then return that particular dog. And obviously you can put a lot more code and logic in place as you may please later on, as you may expect to have. So in this case, you could say we have a public getPet function, and this could be a return of the dog in this particular case. Now, obviously, if you want to play with this, you could have a public, let's say, static, just to emphasize that you can use the interface to call it, and you can say person, and you can simply say a person.play and invoke the play method, and you could do a call with the new dog person, and you could ask the dog person to play with the dog. So that works really well. On the same token, just to emphasize this, we can say class cat lover, and it implements, let's say in this case, a person. And I chose the name cat lover very carefully because in the case of dogs, the love is always mutual, you know that. So essentially in this case, I could say a private cat, and I could say new cat in this case, and you can say public, a pet, and you can say get pet, and you can say return maybe the cat that you want to return, and you could come back here, and you could say, for example, a cat lover, and that could be, so essentially you could provide that implementation like so. Did that go away, actually? The cats mess up really bad, as you can see. Did not like what I said. So cat lover is, of course, implements the person interface, and we could simply say, pardon me, right there. So we could say a private will say, in this case, a cat, and we'll say is equal to new cat. Eventually, of course, this is going to be a get pet, but that's going to return a cat that we have on hand. All right, so let's say in this case, I want to provide this as a cat lover, and we can see that it can work with the cat. So essentially, one idea to embrace really, even though it's a simple one, is to think of interface as a factory method, and then you could have these methods elevated as an interface, and then you could then write your methods, but anywhere your method needs a particular property or a field, delegate that to a method, an abstract method, which then pulls the data from the derived class and pulls it in. So this goes back to a more fundamental question, difference between an abstract factory versus a factory method. So this name was chosen very carefully, as you can see here. So the word factory method alludes to the fact that you have a factory, but the factory is a method and not a class itself, whereas an abstract factory relies on a class that acts as a factory. So here's a way I often think about it. If you're using a factory method, so in factory method, if you're using factory method, then a class, in this case, or an interface, relies on a derived class to provide the implementations in general that you build the hierarchy up. So provide the implementation, whereas the base provides the common behavior that you want to capture. So essentially, when you're using a factory method, you are somewhat standing on the abstraction and looking down on the hierarchy. So you are often relying upon a derived class to really provide the variations, and you capture the commonality into the base class. That's why it's a factory method. So typically, in this case, you can see that the play is a common method we have implemented here, but the delegation of the getPet method to the derived class to really override the behavior and provide an alternative implementation. So you're pushing it down to the derived classes. So generally speaking, in the case of a factory method, factory method, if you will, uses inheritance as a design tool. This is fundamentally how factory methods work. Abstract factory, on the other hand, predominantly uses delegation as a design tool. So if you're using factory method, you are passing message to another object. Typically, factory methods use inheritance. You don't have an extra object in general when you use factory methods. You often have a separate factory object when you're using factory method. So the interfaces and the default methods nicely fit into a factory method pattern, and we can leverage that quite a bit when we start thinking about it as a way of delegating to or giving the control to a derived class to provide the variations of implementation and capture the common logic in the base can be a really effective way for us to push things up into the hierarchy, if you will. So that's an example of how we can think about the factory. So I'm going to go ahead and save this here as a factory method, if you will, and that's basically an example of how you can think about interfaces and of course default methods in general. As factory method could be a really interesting way to approach it. So that's a little bit of a way to think about the functional interface as something useful to achieve that. So having said that, let's talk a little bit about laziness and evaluation. Laziness can be a very powerful tool for delegating responsibility to code that would not have to otherwise execute, and you can improve on performance quite a bit. Well, this is one of the things I would emphasize is a very important capability when it comes to functional programming. And so much so, I want to say that lazy evaluation is to functional programming as polymorphism is to object-oriented programming. So this is really how fundamental this idea really is, and we really want to embrace that. Because without laziness, all we end up with is a cute looking code, but that's not going to perform really well, and we're not going to be really interested in it. So lazy evaluation becomes extremely critical for us to benefit from functional programming. So the question is, how can we embrace laziness? And laziness is is implemented already in the Streams API, but what if we want to do something similar to that in our code? What could we do? Now, there are some third-party libraries, like for example, Waiver, that gives you these ideas. Some of those were influenced by languages like Groovy, but I want to really experience how does it feel to develop something like this on our own, so we can exploit some of these ideas in our design, depending on where we want to experience it. So let's talk a little bit about laziness and how we can benefit from this. So this is going to be the lazy evaluation. So I'll go ahead and push this into the repository here for a few of those. So let's go ahead and try out some ideas on lazy evaluation. So lazy evaluation, I'll just check that notes in there. All right, so let's talk a little bit about laziness. Let's say for a minute we are interested in writing a code which is going to have a computational complexity in it. So I have a public, let's say, we'll call this as compute, takes a number, and let's say for our discussion, this is going to take some time. So we'll say takes some time to compute, right? And imagine, it takes some time. Imagine takes some time to compute. And I'm going to keep it really simple. Let's return a number, times 100. So just a little function. Imagine it takes time to compute it. So I'm going to say in here, some value is equal to 4. And I say if value is greater than 4 and if the compute response for the value, let's say, is greater than 100, then I want to simply specify something like, for example, path 1 I want to take. Otherwise, I'm going to say else we will simply output, and we will output here, let's say, a path 2. So when you look at a code like this, we are asking it to call the method. It says path 2. And just to emphasize this, if I go back here and if I output right there something like a compute called, we can notice that the compute was actually not called. So that's a good news. Now, we all know what this particular feature is called, right? It's called short circuiting. And short circuiting is such a common practice. You don't have to be surprised about short circuiting. Just about anybody who learns programming knows about short circuiting. I think these days children are raised by teaching short circuiting even when they are toddlers, right? You tell them, if you're ever going to write code, learn about short circuiting, because one day you'll be surprised why that function is not called. So we come to realize short circuiting very early on, and so this code did not execute the compute method. But of course the reason for this is you evaluated the value is greater than 4. Well, it's not. So as a result, the compiler said, don't bother really jumping into that branch because this one did not yield the result of true, and it's an AND operation, so it will never succeed even if it executes. No point in executing it. Well, as it turns out, short circuiting is a feature that was introduced way back in time by John McCarthy. This was as old as the Lisp language. So this is pretty ancient if you want to think about in terms of how long we've been using this in our field. So that's an example of what we do is a short circuiting. So that's great so far, but if I go back to this code and maybe I really want to use that value one more time. So in order to use the value one more time, I'm going to say temp is equal to compute value and I store it away. Then I'm going to say over here a temp, and if the temp is greater than 100, and we could say a path 1 width, and maybe I will print out the value of temp right there to display what the value is. So in this particular case, if the value were a 14, for example, you will notice compute was called, and it says in path 1 with 1400, hey, that worked really well. But on the other hand, if I put a 4 in here, what do you think? Is the compute going to be called or not, right? Well, you look at this and say, of course, compute will be called because you're calling it right there. So it was called, but unfortunately, we're not using the result of that compute. How sad that is. That is a waste of executing that function, isn't it? Because we're not using the result of the function, so why bother evaluating that function? Could we just not ignore and move on because you're never going to need it? Well, unfortunately, this is basically what's called an eager evaluation. So this is eager evaluation. And eager evaluation is where a function is evaluated eagerly the minute you invoke it. And as a result, it doesn't wait to see if you're actually going to use the result eventually or not. And that's the nature of languages like Java, is the eager evaluation, which is the default behavior in the language itself. So we saw the eager evaluation, but what if we really want to make this a bit of a lazy evaluation? So in order to do that, let's rethink about this for a minute. And if you ask me, if there is one profound statement in computer science that affects what we do every single day, whether you realize it or not, I would say, if you want to give probably the best award in the industry, hands down, I would say that should go to a gentleman named David Wheeler, who was a computer scientist, a British computer scientist. And he said, I would say, something that is probably the most profound that affects what we do every single day. And he said, in computer science, we can solve almost any problem by introducing one more level of indirection. And this is absolutely, hands down, in my opinion, the most profound observation anybody has made ever, I think. Because if you really think about it, if you want to solve a problem, you often can comprehend the complexity by introducing yet another level of indirection. Now, if you think about what made C language very powerful, okay, very dangerous and powerful. And that was the level of indirection using pointers. And pointers were really a level of indirection because you were able to. So if you really think about it, in procedural code, pointers gave the power of indirection. So this was, I'm not suggesting we all go do pointers from now on, but it's an observation that pointers were a level of indirection in procedural programming. That's what made C really powerful. We're not going to call that function. We instead poke through a pointer and get to the function, right? So that was really powerful way of doing it. And you could say in object-oriented code, we could say the ability to overriding functions gave the power of indirection. So you could override a function. So when you are talking to a function, you're saying, call that function, but at runtime, it doesn't call that function. It calls a function in a derived class. So the function you're calling is not decided at compile time. It's moved on to the runtime. It gave you the power of indirection. And I'm going to say in functional programming, you could say lambdas, give the power of indirection. And I should really say give instead of gave because it still gives. So give, and this is going to be, in the case of functional programming, lambdas give you the power of indirection. So in other words, lambdas give you the ability to postpone a call until you no longer can postpone it. Think of a lambda as like an apple, not a computer, but a real fruit. And if I were to give you an apple, well, there are 4 things you can do with an apple. Well, you could be really hungry and you could start munching on the apple the minute I give it to you. That's one option. You could save it for later. You can put it in your bag and say, I'm going to eat this apple later in the day. Or you can trash it, throw it away, or you can pass it on to the person next to you and say, here you go, I'll share this apple with you and you can eat this instead of me. So just like that, you can do with lambdas like you do with apples. When a lambda is given to you, you could call the lambda right away. or you can take the Lambda and save it for later call. You could throw it away, not use it at all, or you can pass the Lambda to another function. So Lambdas can give you that way of deferring evaluation to a later time, excuse me, and you can just say, I want to postpone evaluation. So to me, I look at Lambdas as a level of indirection, and this really comes down to how you can leverage that level of indirection in the code very nicely. So for example, you could try something along these lines in this particular code, and we can try to use this as a level of indirection. So let's say level of indirection, and how this could be a powerful way to think about this particular code. Pardon me. So let's give it a try and see how we can leverage this level of indirection in here. So let's say libraries like Waiver can do this for us, but I want to really see how this would manifest for something we do. So let's say we have a lazy, and I'm going to say this is a lazy I want to create right here as a class to begin with. And of course, when we are done with it, we don't want the compute to be called after all. If the value is not necessary, that's what we want to really do. So we could say a private, let's say, here's the instance you really want to store away, and you could write a public, let's say, a lazy t. And in this case, if I say, a value that's bringing in, and again, this is not a write code yet, but we'll take one step at a time to get to it. So instant equal to value. And then eventually you could say something along the lines of public t, let's say get, and this could potentially return the instance back to you. That didn't really do a whole lot other than creating a separate class for us to really use in this particular case, but it kind of takes us in the right direction, if you will. Then what you can say is, when you look at this code, that is pretty eager, because the minute you want to pass a value, that got pre-evaluated, and so it's been evaluated already when you receive it. So you're saying, no, I don't want to really evaluate it yet. So what I want to do instead is to take a supplier of t in here. So the supplier of t can come in as a value, and so we can say here comes a supplier, and so we can bring in the functional interface. So we can say function.supplier in here into the mix. So then we can say, I want to store not the value alone, but I'm going to store maybe the supplier, let's say, of t in here as a supplier. So then we can simply say here is this dot supplier is equal to the supplier that I'm receiving as a value. So we'll keep that in there for just a little bit. So then what we do is, when it comes to the get instance, without regard to the concerns of threading right now, what I could then do is to say, hey, you're asking for a get. Let me just say in here, if the instance is valid, I can just produce a value right now. So if the instance is not equal to a null value internally in this particular code, then I could simply say the instance is equal to the supplier.get, get the value out of it, and then I can simply return the instance upon the call. But if the supplier has been used already, I don't want to be recreating an instance after all. I can defer until when it's requested. So then we can come down here and say, hey, I have a temp over here, but let that be a list, a lazy of, rather, a integer, and we'll say temp is equal to. And here's a way to think about it. When you perform a compute, that's a eager evaluation. It runs right away. And you're saying, don't run it right now, move it away for a later. And here is a beautiful way to ask it to move it away. So you're basically saying, do it now, or do it later, right? So that's essentially what you're doing, is to say defer the evaluation to a later time, don't run it right away. So you're able to send it a supplier as a value into this lazy, if you will. So this says, I don't want to call it right away, because if you had done, for example, a value of compute right there, that would be an eager evaluation, as you know, because a compute is run right now before the value is sent to the lazy. But instead you are saying, nope, I don't want to run it right now. I just want to pass this lambda, but the evaluation can be deferred into a later time. I don't need to run that right away. Then you can come back here and say temp.get to get the value, and to call a get in this case to get the value as well. As you can see, it simply said path2 right now. Why is that? Because it came in here and said, I have a temp, but I'm not going to evaluate the lambda until a later time. So this becomes a lazy evaluation right now rather than being an eager evaluation. So obviously, in this case, the path2 never executed the compute. But if you were to say a 14 here, that was a null pointer exception. You didn't see it, right? So essentially, in this case, what I want to do is to call the get function right there and be able to get the value out of it. So in this particular case, we have object instance that's been instantiated. So we want to set the supplier into it, and then we come back here and say instance is equal to the supplier if the value were to exist. Otherwise, we want to return the value that's already there, that's been cached away, so to say, into the instance that we save away here, and we're going to return that value back to the caller. So coming back in here, we are saying I created a temp right there, and when I say a 14, I want to go to the temp and ask for the value get, and that's going to return the value from the instance that should have been cached up here right away, and we want to return at this point. Anyone sees the bug in this code? Equals on this one here. This is going to be double equals. You just restored the faith in pair programming for me. Thank you. Right. This also shows that I can type, but I cannot read. Okay. So let's go ahead and run the code right there. And there you go. Thank you. And path 1 with 1400. And that gives you the result of that call. So that's basically deferring the evaluation, as you can see in this particular code. And then that's not executing at that particular point. So we can bring in laziness. Like I said, you can use third-party libraries, which are much better implementation, but it illustrates the idea of thinking about laziness when it comes to lambdas. So I generally see lambdas as a way of having this level of interaction. And that says, hey, you can execute this code now, or you can execute this code later. So the moral of the story really here is, in general practice, I would say the following. So if you're writing a function, designing a piece of code, you can say, my function 1, and then you can say type value would be an eager evaluation. Versus you can say function 2, and you could take in like a supplier of type, for example, and you could say this becomes a supplier. This could become a nice way to introduce a lazy evaluation at the function level. So when you're designing a function, you can say, do I really want that to be evaluated now, or do I want to postpone the evaluation until the point I really need it? It's not that you would need this every day, but there are times when you may say, I don't bother about this particular evaluation until I really have a reason to use it, especially when your code is going to take multiple paths, and maybe there are paths through which you would never execute a certain combination of functions. Why bother evaluating it eagerly? You can postpone it to a later time, and that's basically what you can do by passing in. So it's not that you have to create a lazy class for everything you do, but the fact is, ask the question, do you want to pass functional interface to a function? So in a generalized term, that's what I would say, when do we pass a value versus a functional, let's say a functional interface to a method? And the answer to that question is, one reason, right, one consideration, I would say, is lazy evaluation. So if I really want to postpone the evaluation of that particular function that I'm receiving, this might be a really good reason to postpone it, and that can give us the laziness, because, again, at a very fundamental level, I would say, think about it as a level of indirection. You are able to push this away to later evaluation, and that can be a very powerful mechanism to achieve in the code in general. So this is lazy evaluation, and then how we can benefit from that. So that's about laziness. The next pattern I want to talk about takes these ideas a little bit further into showing how we could benefit from some of these concepts to provide some nice design ideas. But before I do that, I really need to spend a minute on a slightly different concept here before we dive into it. So let's go ahead and say Decorator, and we'll come back to examples on Decorator in just a few minutes. But before that, let's talk about a few fundamentals. What about Decorator Pattern itself? I'm sure everybody has probably read about Decorator Pattern, even though we may not have actually used it as much. Just as a curiosity, how many of us have heard about or read about Decorator Patterns? A lot of people. Keep your hand up if you actually have used it or just read about it, right? So maybe a few hands go down, right? Well, thank you. So the reason really is Decorator Pattern is one of those scary patterns, right? I apologize for showing you that scariness here, but you probably remember the most infamous example of Decorator Pattern. Remember that? What was that? It's a data input stream. Remember that? And we say is equal to new data input stream, new buffered input stream, and then new file input stream. And so on. Remember that example? Yeah, right? No, you don't want to, I agree. So why is this such a scary example? You look at this and say, you begin to doubt the word decorator. And you think, maybe the word decorator means to make things ugly and scary, right? Because decoration usually means to make things look beautiful. And nobody would want to call that beauty, right? That's a very misguided word. So maybe it's a decorator is to say what it is not. Or maybe decorator means making things ugly. So that's kind of scary. One of the reasons why a lot of us have looked at it maybe, but we don't really use it as much because you're like, oh my gosh, this is nasty. Why would I want to do it? Well, this is where we can benefit from thinking about this a little bit in terms of what lambdas can do. But there's another feature of lambdas that are really powerful we need to spend our time on before we can get into the decoration. So one of the beautiful things is that functions are composable. This aspect of composability of functions is an amazing capability because the ability to compose functions gives us the ability for us to really write a very powerful code in general compared to just dealing with functions separately, if you will. So let's think about this a little bit with a context, if you will. So for example, let's say when it comes to composability, we are really good at this as humans, right? Because this is what we are as humans in general. So for example, if I were to ask you, what is this? I know this a little bit away, but you probably would guess and say, well, gosh, that looks like a pen. And you're absolutely right, it's a pen. But then I could say, in this particular case, I could start removing the parts of a pen. And then I could say, well, guess what we have? That's a little casing that we have separately. And then we have a spring, which is not a framework. And then we have a little, bottom part of it. And I can start continuing to dismantle it even further to the extent where I won't be capable of putting this back together. But the point is, now I say, what is it? You're going to say there's a metal here, there's some plastic here, there's fluid here inside this. And that's a lot of different pieces that we have. Or I can go even further and you can keep going and say, oh my gosh, we got these atoms and molecules and all the things which you can see with a microscope. Or we have a pen. So essentially, that's the beauty of us as human beings is we can abstract things out really nicely. We know that as object composition. So an object is composed of smaller objects, which in turn are composed of smaller objects. But at some level, to stay sane, we say, I don't care about it. Of course, that's called abstraction. So we abstract a level of detail and take things granted at a lower level, unless that's a level we are working in. In a similar way, functions can have composition as well, and it becomes really powerful when we think about functions as a composition. let's entertain this thought a little bit further in here, if you will. So I'm going to say print over here as a function, but this is going to take a number as an argument, but I'm going to pass to it, let's say, a function which takes an integer and returns an integer. And then, of course, I'm going to also pass to it, let's say, a string, which is a message as well. So now, let's go ahead and bring this in as a function star function as the reference. So then, when I come into this particular function right here, I'm going to simply output, let's say, the number given, plus let's go ahead and provide a message that was given to us as well, and then a plus, let's provide a little, let's say, a plus, a func. We'll call the function given to us and call the apply and pass the number to it as well. Just a little bit of code to work with, as you can see right there, right? So nothing really exciting so far. We just provided that particular function. Great. So now what I want to do here is to say a function, let's say integer, comma integer, we'll call it as inc, and this is going to say, given a value, it returns a value plus 1, nothing really exciting. So then what we can do is to say print, and let's say 5, and we'll say incremented, and we will pass to it, let's say, the value. In this case, the increment is the function I want to pass to it. So what's going to happen in this particular case when I pass to this particular function? So you can see in this particular case, well, let me make sure I got this right. Did I mess up with this function already? Pardon me, my ID wanted to mess with me right here. So essentially, I'm going to simply return the number given to us, and I want to return, in this case, the message that we want to display here. Plus, of course, I want to display the value that I'm interested in, which is going to be the func.apply that I want to really return, and the value number given to us is what I want to display. So 5 incremented is going to be 6, and that should be fairly straightforward to pass into this particular function. Similarly, you can take this particular value and you can pass maybe a value of 6, and 6 incremented becomes a 7, so that becomes easy to see. But likewise, you can also say, I want to call this as doubled, and I want to take the value, let's say, and very simple, let's go ahead and double this particular value as well. So you can go back to this code and say, well, I want to take the value of 5, but I want to double it. So we can say 5 doubled is going to be value 10 being displayed. So far, so good. However, what if I wanted to go back to this code and say incremented and doubled? Well, if I want to say incremented and doubled, one little temptation would be to take a value given, and we could say value plus 1 times 2, but that's so boring, isn't it? Because we take the value 5 and double it, and this will not make friends for us, right? So that's not going to be helpful. We definitely don't want to do it. But on the other hand, though, what can I pass in here? Well, if you look at the print function says, give me one function. That's what it says. So if you go to the print function and you pass this one function, it's happy to receive it. You can also go to the print function and you can say, I'm not going to give you that function, I'm going to give you this function. It's happy to take it as well. But the print is not going to be interested in multiple functions, right? So if you take 2 functions, that's clearly rejected, you can see that doesn't work. So essentially, it doesn't really want to work with those 2 functions. When you try to pass 2 functions to it, it doesn't accept it. So what do? How do you really deal with it in this particular case? So this is where the function composition can be really powerful. So let's say I want to take the increment function, and as you would imagine, the increment function is think about it as a box, if you will, and it performs a computation and produces an output. Similarly, the doubled function takes a value and returns a response. But I want to now say, create over here a function, a combined or a composed function. So we can say combined. And what I want to do here is to take the data and pass it to this box, which in turn passes it to the increment function, and which is this guy right here. So we could say here's the increment, and takes the output of increment, passes it then to doubled, where this is the doubled function we are interested in, and takes the output of doubled and then sends it out across. So essentially what you're interested in is the following. You are saying, hey, look, I have the increment function right here, but I have the doubled function right here. But what I want to do is to take the output of increment, but I want to pass it on to the doubled method function, and I want to make a functional pipeline right now. So essentially, you are taking the two functions and you're composing them into one function together. And of course, you don't have to stop right there. You can continue to build even further with this, and you can create a pipeline of a large function as well. But in terms of abstraction, if you ask what you have, you can view them collectively as one function now rather than being two functions. So this can be a combined function rather than being discrete functions separate from one another. Much like how I can take those little pieces and build a pen with it, I can take these functions and build a bigger function with it and compose them together as well. So in this case, I can simply say something along the lines of inc and then. And we could then say, for example, doubled, and that can become a nice way to compose that together. So essentially, this idea of combining functions together can be a very powerful way to create this functional composition, and we can leverage that in terms of decorators and how we can build decorators into our own code as an example. So we'll see that in just a few minutes, and how we can build on these ideas very effectively to use this combination of functions. So again, going at a lower level and looking at functions as these things that can be composed together can be a very powerful way of building applications. So this is, combining functions, as you can see right here. So the question is then, how do we really take this idea further? Well, let's give it a try here. So let's say we are interested in combining functions together. I'm going to create a class called camera right here. And my camera is going to have just a very simple function. We'll call it as a public, let's say, color, and a snap, which takes an input as a color and snaps it and returns it. Again, we'll take a baby step right here, and we'll simply say return the input given for now. So then, of course, this is coming from java.awt.color, let's say, for now. And that's what I'm going to use right here. And we'll build up on this one step at a time, and eventually we'll have a code to execute it in just a minute. But then I want to really be able to compose these functions together as a decorator. So for that, I'm going to say a private, and let's bring in a function right there. So here is a function.function, the same idea we saw a minute ago. And we'll say function. And this function takes a color and returns a color. We'll call it as a filter. So what in the world is a filter? It's a filter not as in filter in functional programming, but the people with fancy cameras, you've probably seen them all over. They have these beautiful cameras, and they can remove these lenses and put more lenses and add filters so they can have different combination of things. So every time I look at somebody with a fancy camera, I have to think of a decorator pattern, because it's really an ability for you to change these filters along, isn't it? So what you can do here is you can say a public camera right there, and this really takes a function color, color, and this could be filters that come in as an argument like so. And we'll see how we're going to work with that in just a minute. And then here you can simply say a filter.apply on the input, and you can return it. So this time you're simply saying, I'm going to snap, but I'm going to take the given input, apply the filter, and return the output right after that. Well, so far so good. But what are we going to do here with the filters? Again, we'll take baby steps towards this one step at a time. So first of all, filter is equal to, given an input, give me back the input in return. We're not even using the filters given right now, so that's a very first step. So to see this in action, let's go ahead and say a public, let's say, a print method like we saw earlier, but here's a camera that I want to pass here, and all I'm going to do is to simply say output camera.snap, and we will provide a color, let's say new color, and we'll simply say 125 as value that's being passed in right there as well into this code. So that's basically what we're going to pass to the snap function. So we'll start with that and see where this takes us. So I'm going to first of all send to it a little camera. So print, let's say, new camera without any argument to the var arg, and simply send that to, it's the same input as output, nothing really exciting. But then I'm going to say in here, I want to take a color, and once you give me a color, I want to send the color dot, let's say, brighter right there. So I want to brighten the color like so. And again, the code is not working yet, but we'll get to it in a minute. Or you can even make it a little bit more concise and simply say, here comes a color, but I want to use a method reference like so, so you can minimize the noise in the code. But I want to use the brighter color. How do I do that? So going back to this code, you can simply say, this is where a little bit of refactoring would be needed. But here's what you can do. You can say filter is equal to, you can say a stream of filters. You can start with the stream of filters. So let's bring in stream.stream right there. So you're saying, give me a stream of filters, and you can do a reduce operation on it. And the reduce operation simply says, I want to start with the function identity, because remember we said give an input, give me an output. That's an identity function. And then I'm going to say, this is going to be a function, and then the one that we used a few minutes ago, we're going to use that particular function. So we are combining the functions into a pipeline of those functions, if you will. And now you can see it's a 178 as an output, because we just basically formed it. So what does this really do? Literally what this is doing is, it is taking all these discrete functions that you provide to it, and it's simply saying, I'm going to put them into a pipeline and form one reduced function of a pipeline. That's exactly what it's doing, is to combine them into a pipeline right there. So now that we combine those functions into one, we are now able to pass the data through that pipeline and do the transformation. So now all of a sudden, you can see in this particular case, we can do the following. And instead of brighter, we can do a darker as well. So you can see that it's darker in color than it was before. Or, as you would imagine, you could also combine different transformations. So color brighter and color darker, and you can put them together as well. And this becomes a series of combinations, if you will. Now, the possibilities are pretty endless at this point. Imagine you have an application where you got data flowing in. You want to cleanse your data. Maybe you want to validate data. You want to throw in encryption or decryption into it. You can pretty much say, here are the different operations in the pipeline, but I want to mix and match them any way I want to. You get the flexibility of a decoration coming in to add them into pieces. So that becomes a really nice way to add in the decorators. So you can provide a core functionality in your application, and then you can add these decorators, any combination you want, much more easily, and that gives you that flexibility, as you can see. And as a bonus, it doesn't look as scary as it once did. You can just pass these lambdas rather than creating this hierarchy of classes. That becomes a lot easier to work with as well. So that is an example of using, in Decorator, using, to decorate, if you will, and that becomes a very powerful way to create a decorator pattern. So that brings us to, again, using lambdas to do a few different things in terms of the fluency of the code you can create and how this can lead to a nice little pattern. And I'll then wrap up with a discussion on how we can use more recent sealed for a design purpose as well. So let's dive in for the next one right in here. So this one is going to be creating a fluent interface. One of the key benefits of writing code using the functional style is the code can be really fluent as well, but we got to put a little bit of effort into it along the way. So let's see how this can help us. And I'm going to give you two examples. The examples are going to look similar to each other, but it's going to give us a flavor of difference This is another point to keep in mind. Multiple patterns may look similar to each other, but the intent may be very different. There are several patterns like that. For example, decorator and composite and chain of responsibility, they all look very similar to each other, and yet they are very different in what they do. Similarly, you could think about a strategy pattern versus a state pattern. They may look identical, but the intent is very different, and so on. So there could be differences in these different patterns, and that can be a bit confusing, but we need to really keep the intent in mind. So with that said, let's say we have this is going to be creating a fluent interface. So I want to save this away here as a fluent interface. We'll call it fluent interfaces, or fluency. Let's save it as fluency. So how does this really look like in terms of fluent code? Let's give it a try. So what I want to do here in the case of fluent code, let's look at a code that we normally write. Let's say we have a mailer as a class. So in this case, I have a public void from, which is going to take address as an argument. And in this case, I'm going to simply return, let's say a from was called. We're really interested in the methods being invoked, so we'll keep it really simple, not do any real work in these functions. So similarly, you have a to function, you have a function called body, and maybe a function called a send, which is going to send the email eventually. So you have a body function and maybe a subject function as well to say a subject. So this can take a line, this can take a content, and eventually the send is not going to take any arguments. So in the send, we'll simply say sending, and in the body, we will simply say body, so we can see it is called. Similarly, in this case, we'll simply say subject, and finally, we'll say to from that function as well. So that's basically what we have so far. Let's see how we're going to use it. So mailer is equal to new mailer, and I'm going to say mailer.from. Well, who is that from? That's going to be from, let's say, a builder at agiledeveloper.com. That is my build system. And it often wants to send me a nice friendly message. It's sending it to my email address. And what does it say? It promptly tells me and reminds me this quite often. It says, your code sucks. And it tells me that. But it doesn't stop with that. It tells me how it sucks, because it sucks different every day. So it gives me the details of the suckiness of my code as well. And then finally, let's say send to send the mail at this point. So you can see that code actually is executing, and this is going to be a to, this is going to be a subject obviously, and then this is going to be a body of the function, and you can see that call come through. But that's a lot of verbosity in the code. I mean, you wouldn't do this, you wouldn't have a good time if somebody sitting next to you keeps saying your name over and over and over. It's like, be quiet, right? That's too chatty. That's not going to be really fun, not a pleasant way of writing the code. But let's come back to that in a minute. So this is a verbose code, not very exciting. So what can we do to minimize the verbosity? So here's an idea. We can go back to this code and breach away from the convention a little bit. And what we will do here is we'll take each of these and return a mailer from each of these calls right there. So you can see that we are returning a mailer from each of these. And so this is going to be return this from each of these functions like so. And except the send function, I don't think we want to really return anything from it. So that's good enough for now. So the code is still working, but we can now come back to this code and say mailer from, and we can remove those semicolons, and we can simply say, here is a mailer, and we can simply go ahead and say a dot on those and just, cascade them together. So in this particular case, we can create a mailer object like so, and then we can remove this right here as well, and you can start cascading them together. So this basically is called a cascade method pattern. So essentially a cascade method pattern really gives us, some people call this as a builder pattern, but a builder is a lot more specific than a cascade method. Cascade method is more general in terms of the pattern itself. So it's kind of cascading through, and you can see that flow that you can attain by writing this code in a very elegant way. So that becomes a cascade method, as you can see. But of course, one disadvantage of this call is, what do we do with the mailer once we are done with it? Should we reuse it? Should we throw it away? It's not very clear what to do with it. Well, this is where we could combine this with lambdas to remove that particular concern. So we'll come to that in just a second. This is the cascade method pattern as we are using it. But let's go a little further with this to remove that burden of the mailer being reused. So we can go to the send method and make it a static method. And then we can say in here, let's bring in a function over here. So here's a function dot, let's say, a consumer. And the consumer that you're going to bring in here, let's say, is going to be the parameter type that you're going to pass to the send method. So we can say here comes a consumer of, let's say, a mailer, and we'll call it a block for now. And within this function, we can simply say, hey, here is the send, and we will simply take this block of code and we will pass a mailer object to it. And here comes a mailer we can create is equal to new mailer, and pass that mailer to that block, and eventually do the sending operation in the very end. Well, that obviously requires a bit of a change. So we can say mailer.send right here. And this becomes a mailer as an argument that we pull in. And we're going to say mailer.from, and all the way down in this call. And of course, we're not going to do the send anymore. And that just becomes a restructuring of it, how we are going to call this particular function. So going back to this code, we can see that we have a consumer mailer, and we can say a block, of course, dot accept, and ask it to take the mailer object and run with it. And one small other detail, we could make the private, let's say, mailer, and the constructor is private, so you cannot create an object of this mailer directly anymore. So the idea behind this is, the code in focus is, as you can see, we have a send which takes a consumer as an argument, and then of course we can call the send method and pass a lambda to it and have that cascade through. And of course the send method itself can say, hey, once you call, I will prepare the object. If I want to reuse the object, I'll take care of it. That's not your concern. So you're no longer interested in creating objects. An object is given to you. You can make use of it and return it. Life becomes a lot easier as well. So you can combine the cascade method pattern with the object allocation taken away from us, and so dealing with object allocation. So the user of the code doesn't have to worry about object allocation at this particular point. That idea of object allocation can be really useful for something else as well, and I will provide that in the next example. I would say this is one of my most favorite patterns, is the execute around method pattern. So what does execute around method pattern really do? So let's talk about the execute around method pattern. So this particular pattern can be a very powerful pattern for removing the burden of object allocation and deallocation from the users of an object. For example, let's say we have a class called a resource. And if you have a class called resource, and this has a public, let's say, resource, and let's simply say output created. So in this particular case, as you can see, the object is being created right in there in the, and we report that it's being created. Then you could say something like resource op1, and this could be simply, providing, let's say, op1, and we could return the current object. And similarly, you could have another method here as well, let's say op2, that you want to write in here. Finally, you have a public void finalize method. And in the finalize method, let's say, release, let's say, external resources. So So what's the problem with this particular code? Well, if you were to say a resource is equal to a new resource, and you were to call resource.op1 and call resource, let's say, .op2. And when you're done with it, what's going to happen when you execute this particular code? Well, as you can see, it said created op1, op2, but it did not really call the finalize method. So if they ever want to rename the finalize method, bad idea would be a better name for it, isn't it? Because that method is not getting called. It's a little teaser. You shouldn't really do this. Now, obviously, that did not work. But I think they had a really interesting sense of humor, because they not only gave you this function, they also gave you a system.gc, which is a pretty interesting function actually, right? Because if they want to rename the GC function, they can call it as a function called hope, because that's what it really is, right? You're like, oh, maybe it'll call the garbage collector. It's like, nah, never mind. So it's not going to really call that either. So that was a terrible idea. In fact, this is one of the reasons why I would say the finalize has since been deprecated. So if you're using finalized, you're going to get a deprecation warning. This is not going to be a fun use. The resource is not being released, isn't it? So essentially, finalize and not called because there's a lot of memory. There's no reason to call it. So what do we do about it? So, a problem to clean up. So you can try a slightly different approach to clean it up. You could say, hey, why don't I call this as a close method? And once I call it as a close method, maybe I can say resource over here, let's say resource dot close, and we could call that method. Now, good news, the cleanup method was called. The bad news is, what if there was an exception? So this is really a problem that's been pushed down. We want to be careful about it, isn't it? So not a good solution, right? Which is to write a close method for ourselves. You could put more patch into it. This only gets worse. You could write a try method, and you could then say, here is the operation you want to perform, and you can write a finally method. And in the finally method, you could call the close method like so. And when you run the code, you can see that it's calling, hey, good news, you handled the exception, but there are two problems with it. The code is verbose and easy to forget to call try and finally. So now you have a bigger burden, right? So if you leave it to people like me, I would forget to call try and finally, and that's a mess again we have to deal with. So that again is not a good solution. You could say easy to forget, and verbose, right? So that's another problem with that code. And I know what you're thinking. You're thinking, aha, but there is a solution in Java already. You could make use of that, right? And that is called ARM, which stands for what is called the automatic resource management. So automatic resource management are also known as try with resources, isn't it? So what you can do here is you can say this implements, let's say, auto-closable. And then, of course, you have a close method already. So that is great. So what you can then do is you can say try, and you can bring the resource in there right away. And then, of course, you can remove this over here, and you can come down and remove the finally as well, and you can run the code like that. That looks sweet, isn't it? So this is called the try with resources. So we could say using ARM seems like an interesting idea. So why not just be happy with it? Well, the good news is the code is not verbose, well, not as verbose, so that's a good news. But the question is, if you forget the try in here, and if you simply call the op1 and op2, let's think about it, right? Remember, the resource has auto-closable in there already. So the question to you is, will the compiler give you an error saying, hey, you should really use a try? I see people nodding their head saying, no, it won't. Right. Will it at least give you a warning? No. What does it do? It just sits there and watches you, right? And so you just look at it and you're back to square one. But of course, this should not be a surprise to anybody, right? Because you know very well deep down in your heart never to trust a feature with the word management in its name. So essentially, that doesn't deliver anything in the end. So this is one of the reasons why I'm not a fan of ARM at all. And I don't use that to, really much because it's easy to forget it again. And that's a problem. So as unfortunately, easy to forget, and we are back where we started, right? So that's one of the problems with this approach is easy to forget, even though it's a tad less verbose. So what do we do related to this? Maybe there's a better way to handle this. Well, here's an idea. We'll go back to the resource class and say this is a private constructor. We'll also make the close private as well, and we don't bother implementing the auto closable. So we made it private, we made it private as well, but then we say a public, and let's go back here and say we want to bring in a function.consumer like so. So now that we brought in a consumer, what you want to do here is to say a static, let's say, void use takes a consumer of, let's say, resource, and in this case, we'll take a block again. But this time around, we can simply say here is a resource, and we'll say resource is equal to new resource. And in the safety haven of the try and finally block, we can then say a resource dot close because we are within the class itself, and then we can say block.accept and pass the resource to it like so. So then we can come down here. We obviously cannot create an instance of a resource because a constructor is private, but we can say a resource dot and use, which takes a resource as an argument, and then we can come down here and say a resource dot op1, and we can then say, here's the op2 we want to call, and then we'll end this. And this is not only concise as the ARM was, you cannot forget and use it in a different way. This forces you to go in a certain path. So I've used it quite effectively, by the way, for managing transactions. For example, typically what I do is transaction.run in transaction, for example, and then I would provide a block of code to execute. So we could say transaction, and I could write the code for the transaction like so. Things like that can be very effective in managing your constraints. And this is called an execute around method pattern because there's a piece of code that's executed before and a piece of code that is executed after. So this is the before part right there in here. So this is the before and this is the after. So essentially, what is this doing really in here? So because you have a before and after, it's execute around a method with a before and after part. So if you really think about it, this is more of a civilized AOP, right? That's what it really is. It's not an aspect of the programming where you have to die after you do it. You can survive actually the journey of applying it, so it becomes a lot easier to work with it as well. So that's basically the execute around method pattern and how you're able to use that here. So this is using execute around method pattern. Like I mentioned, this is one of my favorite patterns. I really like it, and I've used it quite extensively in code. I've written in production. So this is a very, very useful pattern to think about. So the last thing I want to talk about before we wrap this up is one other nice little feature we can benefit from more recent versions of Java, which is you want to maybe close a hierarchy. So let's think about why do we want to close a hierarchy? What's the reason for closing a hierarchy? So imagine you are creating an application where You can provide plugins for others to provide bits and pieces of code to run in your application. Well, if you're going to have plugins come into your application, well, if you're going to provide some interfaces for them to connect with your application, what if they start implementing interfaces they're not supposed to implement? So generally in applications, you have interfaces for others to implement, but interfaces for you to implement internally, but for others to use in general. Unfortunately, so far in Java, we don't have that distinction. If you create an interface, anyone can implement it. And how do you say, here's an interface, but others can only use it, but they shouldn't implement it? There was no direct way to do it. One approach you could take is you could start using reflection and see if the objects are objects you care about, otherwise throw an exception. That's a runtime failure, not going to make you friends. Another approach you could use is annotations, but that's going to make your code expensive to write. You got to maintain the code a lot more. It becomes a lot more, tiresome and error-prone, expensive to maintain. Gosh, there should be a really nice way to control this. Well, actually, we do have a way to control this already, which is using enums. So if you define an enum, it's a closed set. But an enum is great only when your closed set is, so to say, contained, right, into a bunch of constants. So if you're creating constants, enums are great. But what if you're not creating constants? What if you're creating classes, but you want the classes to have a closed hierarchy? Well, this is where sealed really shines really well. You can define an interface for use-only purpose, but not for inheritance purpose. And I think that's a very powerful tool on our hand. So people who are creating plugins for your application can use interfaces to interact with your application, but if they go off and create their own implementation, the compiler will give them an error saying, sorry, you're not supposed to implement that interface, you're only supposed to use it. That would be a really useful mechanism to have. So how would we provide such a mechanism? So really quickly, let's look. They call it sealed classes, but you can pretty much say it's a sealed interface or sealed classes. You can use it for either purpose. So let's say for a minute, let's take an example here to work with it. So let's say I have an interface called traffic light, let's say, .java. And I'm going to say here is a public, let's say, a class interface called traffic, let's say, light. And this interface doesn't have any details in it, but I'm going to say a class called, let's say, red light, and this implements, let's say, the traffic light. And similarly, I have, let's say, a green light as well. We'll start with this as a basic example, and we'll expand this a little bit later. So now I go back to the sample.java and say, in here, I want to create a traffic light, let's say, is going to be a traffic, let's say, light is equal to new red light, and we will go ahead and output, let's say, the traffic light for our purpose. So nothing really exciting, right? So we're just creating an instance of it. However, if I go back to the traffic light in here, I'm going to say a public sealed interface called traffic light. So now you're conveying, and again, going back to what I started with, I want code to be very deliberate, very expressive, and the intention to be very clear. So you're saying sealed interface, I don't want you to ever implement this, but you're most welcome to use it. So in this case, a sealed interface called a traffic light, we provided that right there. So I go back to the code and I'm using that function. Well, in this particular case, I want to go back to the traffic light. Because we are saying sealed, they want you to mark this as potentially one of the different options, but final being a good option. So you're saying, look, I want to close this, so don't go off inheriting from a traffic light either. That serves as a leaf node for us to use in here. So going back to this code, we can see you're able to use a traffic light, not a problem. However, if you try to create a class called, let's say a broken light, and this implements, let's say, a traffic light like so, and I would even go to the extent of marking it final, if you will. But unfortunately, that doesn't work. It says class is not allowed to extend a sealed class, traffic light, as it is not in the list of permitted class. Well, there's an implicit permitted class it uses in this particular case, but it tells you you cannot go off and implement a broken light because you're allowed to use a traffic light interface, but you can't extend from it. Implementation is not allowed. So this gives a nice way for us to take what we already have in terms of like what we can do with enums and create a closed set of constants. Now we are able to create a closed set of classes. What I like about this is twofold. One is it gives a very deliberate way of expressing this in the code. So we're not trying to find out, workarounds to implement something like this. I've got clients who needed similar approaches, and they have taken enormous pain to implement it. Some of their code gives runtime exception, which is not very pleasant because people develop code with it and then find out it doesn't work. That's very disappointing. Or they come up with an expensive mechanism to do this verification at compile time, but that's been several developer hours and a code that's hard to maintain in the long run. And plus you got to write tests around it as well. That becomes expensive. Well, this minimizes the cost very clearly. And the reason is, of course, you simply mark it as sealed and say, hey, you are most welcome to use it. Don't bother inheriting from it. As a bonus, of course, this also helps us to create a much better pattern matching syntax, because if you have different types you are working with, then for the sake of completeness, the compiler can check very quickly if you have handled all the different possible types of values. That can be very effective as well. So this is one of my favorite features in Java these days is the sealed classes and sealed interfaces, and we can very nicely benefit from that as well for what we built. So to summarize what we talked about, we can look at the patterns as predominantly a communication tool more than a design tool, but I really enjoy how we can take a step back and look at patterns again. With the language evolving, I think we can make a better use of patterns in 3 different ways. Some patterns maybe disappear, become natural features in the language. Some evolve to being more lightweight, and a few that we have not had a chance to use before come into play, and we can start using them as well. So those are some of the benefits of thinking about patterns more than trying to just apply them and then enrich our code doing so. Within the next about 5 minutes or so, I'll zip up and post this code onto my website, and the URL will be this, and that will be the some of the topmost link you will see in the downloads page. And I hope that was useful. Thank you for joining. That's all I have.